Hi, my name is Oliver Curl-Grant, and I'm going to give you an overview of the Klarity risk prediction algorithms. At Klarity, we've developed the K-score, a customizable AI-led premature mortality and chronic disease risk prediction model. This model encompasses a pipeline of guided and unguided computational techniques, as well as expert consensus algorithms to find complex patterns and value from healthcare data. And what we're really trying to do here is we're trying to predict an individual's risk of future disease. The pipeline can be adapted readily to any situation using the same philosophy. We have a multi-endpoint ensemble technique, which should deliver the maximum outcome certainty. What that means is we're using as many different computational methods as possible to try and find the best possible answer to any single data question. We're using both artificial intelligence and expert consensus within our pipeline to give the maximum certainty that our answers are correct. As well as giving a prediction of an individual's future risk of disease, we can help to understand what factors it is that's influencing the decision of our algorithm. And via these, we can hopefully promote positive health behaviors. So the way the score works is that we have multiple inputs. We can take inputs from sources such as wearable data, physiological data, for example, an individual's heart rate and blood pressure captured via a smartphone camera, as well as questionnaire-based data. So, the normal sorts of questions that your doctor might ask you about your health. Using all of these things, we can feed them into a machine learning algorithm that has a second layer of an expert consensus-driven algorithm. These two algorithms will work together to give an individual score prediction, which we term the K-score. This gives you a clearly understandable risk of future illness. Different models are available for different disease outcomes. Here you can see the sort of accuracies, sensitivities, and specificities that the models are currently delivering. As you can see, these numbers are comparable to the best available research evidence and are achievable with a simple questionnaire and some basic physiological data. Here we can see a subset of results for our cancer model predictions. These results are attempting to predict the future risk of cancer for an individual over the next 7 years. As you can see, once again, using a small amount of screening within the population, we can deliver an excellent sensitivity of cancer risk prediction. Now, I want to give you an example of how the user will experience the K-score. Here's our example user. This is Mr. Jones. He is a 63-year-old British man, and given that he's an ex-smoker who is somewhat overweight, is understandably worried about his risk of lung cancer. So he completes the K-score algorithm, and he receives a lung cancer prediction as higher. So what that means is that according to our algorithm, we view his risk of developing lung cancer within the next 7 years as higher than most of the population. Now, of course, that's what you may well expect, given that this is a 170 kilogram ex-smoker. That's understandable. What the K-score can provide to him, however, that maybe a simple visit to his doctor wouldn't be able to, is that we can give clear, data-driven, personalized recommendations. So what we can say is we can say to Mr. Jones, these are the exact changes that you should make in your lifestyle, and also the magnitude of change in each area of your lifestyle that will enable you to drive your risk status to lower as efficiently as possible. The reason we do this is that behind the algorithm, you can see that the model is understanding which features in the dataset are most important. So, of course, this is an example in which an individual is worried about lung cancer. So, unsurprisingly, the most important thing may be smoking status, which is at the top left of the graph there. Of course, age is important, alcohol intake is important, but we can see exactly how important each of these things is to an individual, in this case, Mr. Jones's risk of lung cancer. And we can also see by how much we would have to change this feature in order to change the final classification. So we can say exactly to Mr. Jones what changes in his lifestyle we recommend to reduce his future disease risk. On the right here, you can see the efficiency of the model compared to a simple linear model and compared to ideal data. And as you can see, this model is delivering excellent performance. So what the app says to him as the most efficient way to get to a low risk status is to reduce his weight by 5 kilograms. This would in turn reduce his waist size by 7 centimeters. He can go from drinking once or twice a week to stopping drinking alcohol entirely. He can change his physical activity to do moderate physical activity for 10 to 30 minutes a week, and vigorous physical activity for 10 to 30 minutes a week as well. He can also make some dietary changes that are exactly what you expect of a healthy diet, increasing fruit and vegetable intake and reducing meat. However, we can tell him exactly how much we think he should increase his fruit and vegetable intake, exactly how much he should reduce his processed meat intake. So if Mr. Jones does those things over the next year and repeats our test, he'll now be 64 years old, he'll be 5 kilograms less, but he will be in the lower risk category for lung cancer. So this is a very powerful health promotion tool that enables individuals to see exactly what sort of changes they need to make in order to improve their future disease risk meaningfully. Thanks to everyone that's worked on this project so far, many skilled data scientists, physicians, and others who've contributed a lot to what I think is a really great pipeline. Thank you.